I want to apply Newton's method to this function here, x cubed minus x plus 1. So let's take a look at it. Let's plot it. So I'm going to plot f of x for x from -5 to 5. And let's zoom in. So I'm going to zoom in using plot range. And I'm going to zoom in to how about x from -2 to 2 and y from -1 to 1. So what is Newton's method supposed to find? It's supposed to find a value of x such that when I plug it in I get 0. So it's trying to find this number, which is like -1.3, something like that. So it's trying to find a 0 of this function f of x. So let's work on that, and I'm going to do it as another function. Let me call it, how about newt of z? So what's the z going to stand for? Remember that Newton's method, we're supposed to start from some approximate 0, something that we're hoping is close to a 0, and then Newton's method, in theory, should be getting us closer and closer to a 0. Hey, in practice, what we really hope is that eventually it gets close to a 0, but in the intermediate steps it might get further away from this -1.3 here. So what's this going to look like? Let me do a nest list, and I'm going to apply Newton's method 5 iterations. So that's what this 5 stands for. My starting value is going to be z, the input to this function that I'm writing. And here I have to write some pure function that represents Newton's method. So remember what Newton's method looks like. If you start with z, then you want z minus f of z over f prime of z. But we can't do it this way. Like, let's try this and see what happens. Say I do newt of -1.2. Okay, so I'm starting here, starting at that value. Okay, so weird stuff happens. I get this parentheses and a number and then a bracket, -1.2. And what's the problem here? Problem is that I'm supposed to use a pure function here. I'm not supposed to use any variables. So I replace all of these variable letters with a pound sign. And don't forget that you finish off a pure function with the and symbol. So here you can see that I started out close enough that I got very close to an actual 0. For example, if I do f of this -1.32472, I get a very small number. You might wonder, why did I not have to use capital N anywhere for the numeric approximation? And the reason was that when I input a number with a decimal, that decimal is telling Mathematica that I'm doing approximations. So everything that it does, it's not trying to do it exactly. It's doing some numeric approximation for the numbers. So when you're inputting something with a decimal, you don't have to worry about putting a capital N anywhere for the numeric approximation. So what would I like to know? I would like to go through each starting value from -1 to 1. Okay, so each starting value here, I would like to apply Newton's method 5 times, which is what this newt function is doing. And then I want to analyze how close do I get to zeros doing that. So let's work on that. Let me delete a couple of these. So let me make a table, and then I'm going to do newt of z for z from -1 to 1 going up by 0.01. So total this is going to be about 201 little lists. Okay, so there we go, and each time it's ending with this, that's a good sign. That means it's getting close. But not always. Like, for example, this little list, that one didn't get close to a 0. And if all I care about is how close does it get at the end, then I really don't need to do the list, which is what makes these inside lists. It would be fine just to do nest instead of nest list. So let's try that. So now it's not a list of lists anymore. Now it's a list of the final values. So now it's a list of how close did I get to this 0. So let me name this something. Let me call it, how about my table? And I'd like to know how many entries in my table are close to something that I plug in to get a 0. So let me find that with count. So let me count inside of my table. And what do I want to count? I want to count x's such that if I plug in x, I'm close to 0. Well, how do I say close to 0? Let me do absolute value of f of x less than, how about, 0.001. So this is going to tell me out of the 201 entries in my table, how many of them, when I plug it into f, the function I'm trying to find a 0 of, am I less than 0.001? So for how many of them am I this close to a 0? So this says 30. That's pretty good. How about how many of them am I really off? Well, let's see what's the maximum value that I get. So let's make, how about something called new table? And let's go through my table and just look at absolute value of f of z. And this is for z inside of my table. So this goes through all those final values, plugs them into f, and takes the absolute value. So everything where I see times 10 to the negative 10th, something like that, those are all really small, so those are all good values. What's the maximum that I get? So it's definitely not the case that applying Newton's method 5 times always gets us close to a 0. This is saying that there is some value between -1 and 1, where when I apply Newton's method 5 times, I get either 472,000 or maybe negative 472,000. You might wonder why some values are so bad, and the reason for it is, imagine I plug in an x like this. Then Newton's method, it's all about taking tangent lines to the graph, and here the tangent line, it's going to be really close to flat. Probably won't be exactly flat, but will be close, and when I evaluate where that crosses the x-axis, it's going to be some gigantic number.